Okay, now let's take a look at this next one. This next one is just by looking at it, I already know what series test I want to use because the only series test that truly works for this one is this is the alternating series test. So what does the alternating series test say? It's that if I can if my series if I take away the negative part or the oscillating part of my series and just consider this piece that I'm going to call A of n. If A of n is decreasing, which means that the B of n plus 1 term is always less than the B of n term. What does that look like? Well, if I say this is my B of n in the sequence, then my B of n plus 1 must be less. So it's a decreasing sequence, which makes sense. But this is just how we write it in more uh, formal terms, is that if the B of n plus 1 is less than B of n, then and it's always less, then it's always decreasing. So it's decreasing. And the other condition that must be met is that so an has to be decreasing over the interval. Next thing is that not only does an have to be decreasing, it has to be decreasing to 0. So the limit as n goes to infinity of a of n should be 0. And so what does this look like? If we take just an and try to plot it, we're kind of checking for this condition. We want it to go to 0, okay? But the only thing here now is because if we are able to check that a of n goes to 0, then we bring back this alternating negative piece, then I'm technically saying, okay, I have one positive here, one negative here, one positive here, one negative here, positive here, negative here. But look what happens. As my n grows to infinity, each positive and negative is slowly canceling each other out. And that's what we really want in a convergent series, because that means that each piece is canceling each other out, and so it will probably add to a finite number. Okay, so let's check that these conditions are met. Let's check if they're decreasing first. So if you want to show decreasing, there are a few ways to do so. I mean, this one's a little hard because it's not exactly obvious what the function looks like. So the best way to show decreasing is actually just to show that over the interval, as because we only care about sequence behavior from n is equal to 1 to infinity. So from 1 to infinity, we just want to show that the derivative is negative. Because what does the derivative being negative mean? It means that it's always going down, right? So that's exactly what we're looking for. Let's try to take the derivative of this equation. Okay, so just looks like probably a quotient rule. So 3n squared minus 1 times n4 plus 1 minus n third minus 1 times 4n third. Oh, sorry. This is not 1. 4n third. Something like that. Over n4 plus 1 squared. So looking at this, it's not exactly clear what it's even doing. So let's see. I know that this will always be positive, so I don't have to care about that. Let's look at the top, though. When I multiply this out, I get 3n to the 6th plus 3n squared, and all of that minus 4n to the 6th. Plus 4n to the third. Okay, let's just look here. These ones will almost never grow. These ones will never grow as fast as the n to the power 6. So we can just kind of put these behind us. We'll just consider the negative 4 to 6, 3n to 6, plus maybe like 4n third plus 3n squared. So we can ignore these terms. Let's look at these ones. If I simplify this, I get negative n to 6, and that surely after some really big n will overpower this. And so what does that mean? That means my derivative will always be negative, because this will always be negative. And so the first condition is met. So we need to, the alternating series test is hard if you don't know what the function looks like, because you have to make inferences about the derivative and try to guess like, oh, will it actually always be negative? And so I hope I was able to show the process of how you decide if the function is decreasing or not. But we agree that the function is decreasing because the derivative is negative, because it is a negative n to the power of 6, essentially. Okay, so let's check now that the limit goes to 0. So this one's a little easier, more straightforward. So limit as n goes to infinity, n to the third minus 1, n to the fourth minus 1. Right now it's not obvious. We plug in infinity, we get infinity over infinity, so we get an indeterminate form. So we have to do a L'Hopital's rule. If I do L'Hopital's rule, I get 3n squared plus 4n third. The ones cancel out. And look at this. We can say that this is equal to 3 over n squared. N, 4n. And look at this. When I plug in, if I take the limit as n goes to infinity, I get 0. Because this will grow really fast to infinity, but the 3 will just kind of be very small in comparison. And so if you have a very small number over a very large denominator, it will go to 0. And so by the alternating series test, we know that our function will our series will have this behavior and slowly converge to a finite point. And so yeah, it's a convergent series.